Hey everyone, how's it going? Round of applause for everyone back there who's helping making this happen today. Hedge, I like to do this thing and I just kind of like chill and like look at the cat. And like the longer the talk is, the longer I'll do this because I have time to burn. But it kind of started as this thing that I did to just get myself loose on stage and get comfortable. And it slowly turned into an audience test. So like I have my back to you and I hear how much you're laughing. And I know how painful this is going to be because if this doesn't work for you, well, it's going to be fun. So I'm Myles, and I'm a developer advocate at Google Cloud Platform, mostly focused on the Node.js ecosystem and our various compute offerings around Node. I have a laser pointer. I'm going to use it to point at that. I'm not representing Google on stage right now. This is just mostly, things I think about late at night. So, chapter 1, asynchronicity is hard. So you don't want to stop the thread. And I think, as people who are working in the front end, you notice this maybe a little bit faster than people who are writing servers, or probably you've noticed it in both. But, if you block the thread in the browser, it's going to stop scrolling, and that's a pretty bad user experience, in my personal experience. On the back end, if you're trying to make, if one user's coming in and making a request, and that's blocking the thread and blocking the server, like the next person is just kind of waiting. And I have a feeling you don't want to be dealing with your user traffic sequentially. So in JavaScript, we have a bunch of different ways that we've created for handling asynchronicity. And traditionally, one of them is callbacks. And I'm pretty sure most people in the audience have used a callback before and seen code like this that slowly floats to the right. I know there's a lot of slides like this online already. I made my own take on it. But to deal with kind of some of those problems with asynchronicity and things floating to the right, we've adopted new patterns. Promises are a pattern that have actually existed in computer science longer than JavaScript, believe it or not. But it's fairly recent that it's been standardized in the language. There's a number of different implementations you may have used, such as Bluebird, but now you don't need to worry about a dependency. You can just use the promises that come with JavaScript, and because of that, the virtual machines can make them really fast. And that code before can start to look like this, which is better from like a mental model perspective, arguably, when we're thinking about like handling asynchronicity. The ability to catch and kind of do a catch through a whole bunch of promises that all pipeline together is a really nice pattern. We don't have to kind of consistently be error handling the way we do with callbacks. Although, controversial whether or not this is better than the callback pattern, but at least things aren't floating right anymore. But we actually still have a lot of callbacks here. You don't really separate the two. But in December of 2016, a new pattern came out that I personally really loved called async await. And just quickly in the audience, how many people have played with async await yet? Right on. It's kind of a game changer in my personal opinion. It's a much more intuitive mental model for thinking about asynchronicity, and the same code looks like this. And there's a couple things. This is kind of both like the future and the past at the same time in this really weird way, where we've got this kind of like immediately invoked function expression thing going on, which I don't know about you, but when I first started programming in JavaScript, there was that immediately invoked function expression from jQuery that I just copied everywhere. I didn't know what it did, but I knew that I needed it. And then we have try and catch, which are some friends we haven't seen in a while, but they're back, and they're back for good. But so, that was kind of this really high-level example of these patterns, but I thought I would give a bit of a practical example in use. So here's an example of an implementation using callbacks. To get at the Node.js download page, we have an index.json, which has all of the metadata for all the releases we've ever done. And this is an example of using request and callbacks to get the version and the date of our latest release. And so you could see we've got some kind of manual error handling there. We have this function here. We have the data. But there's a couple things here that are important to think about. One is we've started floating right. We haven't had to do it too much. You notice that body sort there is another function that could have floated right as well, but I've broken it out. But the data that we have about the body, the version, and the date is inside of the closure of that callback. It's not accessible in the outer scope. It can't be exported from the module. It's kind of stuck in that closure. With promises, we can refactor the code, and it gets a little bit more streamlined. But for this case where we only had like one instance of asynchronicity that we're dealing with, the pattern is not that obvious. But we've moved to the fetch API here, so you can see that we've got a couple promises happening one after the other, specifically here to like fetch the resource and then convert it into JSON. Now, this promise code can be refactored into async await, and it looks like this, which is better, maybe, but when we're thinking about JavaScript from an educational standpoint and from a pattern standpoint and an onboarding standpoint, all we've really done here is just tack on more and more concepts that people need to know to sit down and use this. And by the hands in the room, I'm going to assume that the majority of people here, this just kind of makes sense off the bat. But if you think about the things that we need to know, we need to learn what a function is. Then we need to learn what an async function is. We kind of still need to know what a promise is, because to execute the async function and do any error handling, we need to still have a catch there and manage that promise. And we still, I guess we've kind of hidden callbacks here a little bit, but there's still a lot of different concepts that we need to introduce before we can just introduce the concept of let's do something sequential. And the same code with top-level await just kind of removes that async function, but all of a sudden from an education standpoint, from a getting started standpoint, from a readability standpoint, at least in my own opinion, we've removed a lot of abstractions that you need to learn in order to just understand, hey, that first line is going to run, and it's going to do something asynchronous, but that second line won't run until the first one's over. And this is a pattern that I'm really interested in seeing happen, which leads us right into chapter 2. Don't tell me what I can't do. So in February of 2017, Node released 7.6, which included V8 5.5, which was the release where async and await first landed. Now, it came out in December in V8. It took us a little while to get it out in a release, but we had it. I was excited. I was ready to play with it until I got this error. I don't know if any of you had seen this, but I had not gone through and read all the docs about async await. And for someone, I use the language a lot. I'm following the standards. I probably should have known better, but I didn't. And I was very surprised, and it was unintuitive that I needed to have await inside of an async function, and this is kind of how I felt. And it looked like top-level await wasn't a thing, so I started digging and I started playing, and I have this saying that I've been iterating on, that people work to the abstraction boundary in which they're comfortable with to try to fix things. And since I am comfortable in Node, I tried to just implement top-level await in Node. And so if you look here, it's probably hard to read back in the back. I apologize. But we've got a one-line change in Node.js in our Bootstrap Node module. We do this really fancy thing where we take the module code that you give us and we do a string concatenation, and we just wrap it in an immediately invoked function expression. And that's how we inject all the variables like dir name and file name and require and exports into your code. So if you've ever wondered how that happens, it's this fancy string concatenation. So if you actually close the brace at the beginning of your code, you can break Node in really weird ways. But so I thought, OK, maybe I could just make that an async function. And maybe that will work. It didn't. It turns out that when you turn a function into an async function, you immediately turn it into a promise, which means that it starts getting executed at the next tick. And since all of the different functions in Node are expected to execute in a particular order, this completely messed up all the timing of everything in Node. So it just completely broke require. It didn't seem, for example, the top-level await was something that we would be able to implement in Node Core, unfortunately. And it turned out that the Node.js test suite wasn't the only place that had a problem with top-level await. Because it turns out that some people think top-level await is a foot gun. Has anyone in the audience heard that expression before? Top-level await is a foot gun? I guess before we dig in, a definition of a foot gun from Google. A foot gun, plural foot guns, informal, humorous, derogatory. Any features whose addition to a product results in the user shooting themselves in the foot. I like this idea from like a user experience standpoint, which is like a foot gun is any feature that will likely be used for people to hurt themselves. And I'm all about like being given all of, I want to get into trouble. But there is this weird balance as a platform developer. And when you start thinking about designing APIs that people are building APIs with, about like how much leeway do you give people? How much opportunities do you give them? You don't need to implement every API. You just need to make things possible. And small fundamental changes, like something like top-level await, can have very, very deep impacts in the language and the runtime that may not be obvious. And in September of 2016, a year before async await even made it out in a release, Rich Harris of the New York Times, you may know them from such amazing products as Svelte and Rollup, wrote this really informative gist called top-level await is a foot gun. A gist that would be brought up whenever I mentioned top-level await. And the TLDR of that gist, if you haven't read it, is that top-level await could block execution. If an await is no longer inside of an async function, what do? You just kind of stop executing things. So is that going to block the whole thread? Is that going to block the execution of the context? Is that going to, how does that work? That needs to be defined. Top-level await could block fetching resources. So depending on how the module loader itself is worked out in the runtime, is calling await going to block fetching resources for other nodes in the graph that haven't been fetched yet? It's possible that there would be no clear interop story for CommonJS, which is the module loader that we use in Node. And as you saw from my prior example there, it was very clear that this was pretty true. It wasn't easy to introduce top-level await into Node.js without completely changing all the semantics of how things run. And it's also possible that circular dependencies utilizing top-level await and dynamic import could introduce deadlock into your graph if two modules are relying on each other and never resolve. And the conclusion of this gist was, hey, for all these reasons, can you not? Can you please not top-level await? And a lot of the rhetoric around top-level await at this time was very much, it will never happen, it should never happen, can you not? But I wasn't ready to not. I wanted to. So a little bit of history and how you approach problems like this. So when you go online, it's really easy to kind of see all these flame wars that are going on. It turns out, though, that flame wars are not canonical decisions for the JavaScript language, thankfully. What you can do, though, is you can review the notes of TC39 meetings, which are all available at that link, tc39/agendas, and they're all in Markdown. And you can go and use your favorite text editor of choice or the command line in grep, if you so choose, and search for the keywords of the things that you care about decisions on. And from a canonical level, if things have not been decided or stated or mentioned in these notes, it's maybe fair game. It doesn't mean it's going to work out the way you want it to, but you can try. And what I found when digging in was that despite the strong critique of top-level await, there was actually no prior decision that banned it from ever happening in the language. In fact, when going through, I found out a few things that prove that maybe top-level await is a thing that should happen. So when await was originally brought, async await was brought to TC39, it was in January of 2014. So we're going back a bit further now. And in April 2014, it was decided that await would be a reserved keyword in the module goal. Goal is a term that has to do with a combination of the execution. I won't dig too much into it, but you have a module goal and a script goal. And you can pick between different goals, such as the sloppy goal and the strict goal, by using useStrict. The module goal happens when you use a script tag with type module. Otherwise, you're in the script goal. But inside the module goal, the keyword await was reserved. So the only reason this would be reserved as a symbol would be if it were going to be used at the top level. And in July 2015, async await was moved to stage 2 in the process. And at that time, it was decided to delay the decision about top-level await. It was so contentious that simply trying to make a decision about top-level await would have blocked the entire async await feature. And you're going to notice a bit of a pattern here that happens in the standards. If there's some part of the implementation that can't be agreed upon, but it doesn't necessarily get in the way of doing a smaller subset of what's being worked on, you just push that thing off. Don't deal with it. So async await moves forward, and as we can see from the hands in the crowd, it's a beloved feature, but this particular decision, which could have blocked it from ever happening, was just decided, to be dealt with later. But the important takeaway from all of this research was that top-level await was always being considered while this was being standardized, and further, things were standardized in the language to protect for it to be a possibility. So, there is a chance. But I just said a bunch of things about how we put together standards and maybe a few phrases that don't entirely make sense without context. So let's add a little more context and talk about how a language babby is formed. So the spec is called ECMA 262. And the committee who implements it is TC39. So we have JavaScript, the language, which is actually called ECMAScript. It's standardized in ECMA 262 by a committee called the TC39. And the committee meets every other month at locations around the world. And participants include major browser vendors, academics, industry experts, open source maintainers, and maybe you. And you may be asking this question, can anyone join TC39? Who can join? And so there's actually a bit of a difference between a member and a delegate. A member is an organization that sponsors ECMA. And ECMA is the European Computer Manufacturers Association. It is a nonprofit based in Geneva that handles a number of different standardizations, not just including JavaScript, but C# is also standardized there, as is the width of a CD-ROM. Important standards that have modernized society. But seriously, I think Dart is standardized there as well. They're doing some stuff around AI. There's a lot of different standards, and there's this whole kind of back end to the standards process that you don't see that involves actually lobbying governments and making sure that the things that they're doing are approved by ISO. And there's this whole kind of bit like releasing software that you just don't see, but it costs money to do. And so various organizations, such as my organization that I work for, Google, or academic institutions like a number of different universities, can all join ECMA, and they have a sliding scale for membership from free for nonprofits and education institutes to not free for organizations like Google. And there's a sliding scale that's based on how many employees you have. Individuals are not members, though. Individuals are delegates. They go to represent a member organization. And as long as you are part of an organization that's a member organization, you can go, as long as you can navigate the internal politics of allowing you to attend. As an individual, you can be an invited expert. And I've seen individuals from the Babel project, for example, show up. And the real only way to do that today is by being involved and knowing the right people. But there's a number of people involved in ECMA, including myself, who are trying to make a documented process or a more streamlined process for individuals from the community who have proposals that they want to work on to identify champions to help drive that proposal forward for them and find opportunities to come and potentially even get sponsored financially to attend meetings to work on their own proposals. But so that's a lot about kind of the structure of ECMA, but how does a feature itself get developed? It's all through consensus. And consensus is this really interesting and terrible thing at the same time, whereby you need to get everyone in the room to agree to not disagree. So the whole concept of consensus is making sure that no one dissents. So you've got a room at TC39 with 50+ people representing a ton of different organizations. So, at one corner of the room, you may have Microsoft, then you have Google, and then you have some academic hackers, and then you have people who work on embedded systems, and then you have LinkedIn, and then you have Bloomberg, and I'm not just going to list member companies, but you have a lot of different stakeholders with different needs. And for a feature to move forward, you need consensus from every single person in that room that they see nothing wrong. So every single feature that you've seen land in JavaScript after ECMAScript 5 has gone through this consensus process. And there's a number of stages. So the first stage is stage 0. It's called the straw man. And this just means, hey, I've got an idea, and I'm sharing it with people. It doesn't necessarily even mean that the committee agrees that this is an idea we're going to explore, but it's like, here's kind of the shape of the problem. Stage 1 is a proposal. It means that not only do we know the shape of the problem that we're trying to solve and a potential shape of the solution to it, but the committee agrees that this is a problem space we want to explore. Stage 2 is a draft. By stage 2, not only do we have a very, very strong idea of the problem space and the solution, but we have gone into the solution and come up with specification language about how the algorithm for that solution might look like. Stage 3 is a candidate. At this point, that solution, that specification text, has been solidified, it's finished, it's been reviewed by at least 2 other committee members and signed off by the editor. When a feature reaches stage 3, at this point it's ready for runtimes to start implementing it. Now, tools such as Babel, or maybe even runtimes such as V8, may implement things that are stage 0 through stage 2, but it's not really until something moves to stage 3 that you know that the shape of the solution isn't really going to change, that the API is not likely to change. Now, we've seen times where this has been pulled out from under us. Smoosh is a really great example of this. So if you're writing code using Babel, for example, and you're using any of these stage transpilers, unless it's stage 4, which is finished, which means it's in the spec and it's in the language, these can change from under you. So just kind of be prepared for that. But it also is, like, I'm not trying to discourage you from trying these things out. It's really great to have people trying out these language features early in their life cycle so we know how they're working. We find edge cases early. But just kind of an idea of how this works. And each of these stages for a feature to go through needs consensus of the committee. Which brings us into our next thing, getting a foot gun in the door. So I hatched a bit of a plan here. And the idea was if I brought top-level await to TC39, we could at the very least get a decision. And even if that decision was no, we could at least stop all of the arguments. And so when I was thinking about like optimization and how many hours we were saving of like development time on the planet, there's one way where you could say, oh, well, I'm optimizing asynchronicity and I'm making it way easier and there's all these hours of development time we'll save. The other side is, oh, we'll never do this, so that's like 1,000 hours of Hacker News time that's not going to happen anymore with people arguing about this. And in January 2018, I brought top-level await to TC39 attempting for stage 1. The proposal included a handful of different things. It included the history of top-level await that we had just gone through, showing that the committee had presented interest in it in the past. Motivation for the feature, why are reasons that we would want to do this? Use cases, how it would actually be used. Potential implementations, so a couple different algorithmic solutions to how we could approach the problem, as well as constraints. And this was one of the most important things to bring. Early in the process, it's actually really important for you to identify all the reasons people may object to your proposal. And you may not have answers to them, but at least you have to show that you've thought through the problem space and none of these things are a surprise to you. So one of the motivations that I had was the immediately invoked async functions expressions. This. It's kind of gross. And while it's not such a big deal to just write 2 lines to wrap your async function, there's a couple limitations that come from this. First, when we're thinking about executing code in the graph, which we'll dig into a little bit more later, if the bodies of all of our graphs are wrapped in these async function expressions, we have no actual idea of the order of execution of things in the graph. One of the reasons why people were saying we shouldn't have top-level await to begin with. So if this pattern is getting cargo culted and is showing up all throughout your graph, it's actually introducing asynchronicity to bodies that may not even need it. People may be introducing these async function expressions and then never even using await in there, simply because they want to be able to when they're going to need to. Also, any symbols that happen inside of this async function expression are not exposed outside of the scope of that function expression, unless you're lazily loading them. And if then you're exporting lazily loaded symbols, you're introducing a whole bunch of new, really weird race conditions where all you wanted to do is say, hey, don't export this symbol until this thing is done. So this was a huge reason that I pushed for it, was this pattern. A second motivation for it was the completely async module. So if you thought immediately invoked function expressions were bad, wait for this. Imagine people exporting default async functions that in turn then await importing async functions that they in turn then export. And you may say no one would ever do this, but if you actually search on GitHub for kind of the base pattern here, you will actually have more matches than you want to see. There's a lot of people who have already started exporting async functions, which are fine unless you start falling into this pattern. At this point, we've completely gotten rid of any sort of static module system, and the whole idea behind ESM has kind of fallen apart. So why would we even want to do this? What are the use cases that we'd have for top-level await? One of them, right off the bat, that we can think of is dynamic dependency mapping. Let's say we want to import a version that's specific to a language for internationalization. That would be really great if that's something that we can do dynamically at runtime. Resource initialization. I don't know how many people are doing things with databases or robotics, but sometimes you need a serial port to be open before you do anything else. And if anyone's ever done those kind of like intro to robotics classes, literally the first thing we need to teach someone is, hey, here's a promise or here's a callback, not, hey, open a port and do a thing. And all of a sudden you get really into kind of the mechanics of JavaScript of a language before people can even start doing things. And things such as being able to await a database connection, I personally think, is a really powerful pattern. We have that pattern in Node with require, because require is synchronous and inline. And with ESM as it exists today, you do have dynamic import, which we will see on the next slide. But you're not able to take those symbols that you dynamically imported and export them in the same way that you can with Node. So if you wanted to do something like dependency fallback or any sort of CDN-related stuff, this isn't really something that you can do as symbols that you're going to export from a module. These are a variety of patterns that I think top-level await would unlock, but not all of them. So we start getting into solutions and potential solutions. How would we solve this? What would it look like? And the first way that we talked about solving this was variant A, which is the idea that a call to top-level await would block execution of the graph until it had resolved. And if you thought about this code right here, where you're importing A and then B and then C, and you log them, and modules A, B, and C all have a call to top-level await in them, it would kind of be the equivalent to this, an immediately invoked async function expression where we await A, and then await B, and then await C. A has a top-level await in it, so we're going to wait for A to resolve and export its symbol before we start executing B. The other variant that we talked about was variant B, where a call to top-level await would block execution of parent nodes in the graph, but would allow siblings to execute. So the same code from before would start to look like this, where we would be awaiting a promise.all of A, B, and C. A would execute until the point that it hit a top-level await. It would then defer, and B would begin executing. This has the advantage that if you are doing things like component systems that would be very, very wide but not very deep graphs, you don't have to wait to lazy load component A before you can lazy load component B, before you can lazy load component C. And if you're working in a component system where you may have like hundreds of components wide, if we did variant A, that's really, really not going to work for dynamically importing any sort of components. The difference here, though, is this is introducing some indeterminacy, which we'll dig into in a second. We did talk about an optional constraint that could be applied to either A or B, which is enforcing the top-level await could only be used inside of a module without exports. The idea being, if you are using a module that doesn't have exports, you're either going to be just the root node of the graph or a module that's only being imported for side effects. And in those cases, you kind of are just like locking that leaky abstraction to a point in the graph. And we'll talk a little bit about that in a bit too. But I just used a bunch of terms talking about async and loading and execution order. And it's not very intuitive to just hear as words, so I thought maybe I could dig in a little bit more with more words. So ES modules specify an asynchronous load and a synchronous execution. What this means is that the first thing that happens is you do a load. You fetch all the resources for the module graph and resolve all the specifiers. So every single import gets resolved. You figure out where that resource is coming from, and you fetch that resource from over the network. And the whole graph is populated with all the resources that are statically imported before anything else happens. And it's all asynchronous. So if resource A is loading and resource B is loading, they can happen at the same time. And once that resource loads, we figure out all the symbols from that, and we just kind of go through and fetch the whole graph. If you're calling the same symbol multiple times, it gets cached, and you don't have to fetch it more than once. After it's been loaded, it's linked. And for a link, that modulo graph must be in memory, and that linking is happening in a pre-order traversal, starting from the root, then the left, then the right. This link is how we actually build up the graph, work out any cycles, and actually figure out how all these different records that we just fetched connect. So here's a graph with a root node, module A and module B that are imported by the root, and module C and module D, which are imported by A. So when we're linking, the first thing that we're going to link is going to be the root. Then we're going to link A. Then we will link C. Then we'll link D. And then we'll link B. Not very intuitive, but thankfully this is mechanics, internals. You should never really have to know about this part of the graph traversal. But I thought that kind of visualizing it would maybe help. So execution, once everything's linked, and we have all of the modules in memory, we can actually start executing your program. And it requires that everything's linked, and it's done in a post-traversal order. And this is, I think, one of the most confusing things about ESM that people are not expecting. So here's your graph. And if you were writing something in Node, you may expect that it's going to start executing the root, and then when it hits the module that it imports, it will start executing that. But ESM forces you, by the spec, to have all your imports at the top. And because of that, it actually starts executing at the bottom left. C will be the first module that gets executed in an ESM graph because all the symbols from C need to be exported before A can be executed. So next will come D, and then A, and then B, and then the root. So this is the order that your code's actually executing if you're using ESM and you're using native ESM. Not if you've written ESM and you've used Babel or Webpack to transpile it to require and then to something that's synchronous in the tree in a single bundle. In that case, it will actually be from the root. But ESM, as it's standardized, this is the execution order that your code will go in because you need the symbols from your children available when you execute yourself. And here's where things start to become a little less intuitive. So we finish loading, and we kind of come back to that thing that we were talking about with variant A. And so if we look at this graph again and we think about variant A, and let's say that C here has a top level await, C is going to be the first module that starts executing, and we're actually going to wait for that top level await in C, the deepest node in our graph, before anything else will execute. And this is potentially quite problematic if you have a really, really deep graph and one module at the bottom has an await in it, it can block the execution of the rest of the graph. It's worth mentioning that this is different than blocking execution on the thread. Anything that's already in memory, anything that's already in the event loop, will actually be doing its thing. It's only the traversal of the graph that would be blocked. So to variant B, when we were talking about a call to top level await, blocking execution of parents, but not siblings. And we look at it again here. And let's say, once again, C has a top level await. C would defer, and D could start executing. And when D is done exporting its symbol, A would be deferred because it's waiting on C, but B could start executing and export its symbol. And at the point that C was done, then A could start executing, and then the root could start executing. And so you could see how this unlocks a problem for execution order and for some of the problems that may be introduced from speed. But it introduces a new problem that didn't exist before. We had a guaranteed order that the graph would execute and always execute. And if we introduce variant B into the specification, we fundamentally change the underpinnings of the JavaScript language and the expectation of execution order. The only real strong argument that I have to this is that most people wouldn't know the execution order to begin with because it's not very intuitive. I don't know if that's strong enough, and we have to work out a bunch of models to really figure out if this will bite you. Because if you're doing anything that's messing with global state and expecting that order, it can introduce really weird, unexpected errors, which are kind of the worst kind of errors. But we identified a handful of different constraints here. First, that variant A would halt progress in the module graph until it was resolved, that B would halt progress but not block siblings, and that optional constraint that we were talking about could alleviate those above concerns, but it doesn't really solve it, especially since any module could be imported. We also have that constraint that we talked about, that circular dependencies could introduce deadlock, and we didn't really have a solution to that. But to the concept of blocking. We brought up that there's actually a handful of ways to already block progress in JavaScript. The good old infinite loop, that one gets us sometimes. Infinite recursion for when infinite loops are not good enough. Atomics.wait for when you want to use an API you've never heard of. These are all different ways that you can already halt progress in JavaScript. And so just bringing up these examples as a response to the halting progress being a reason not to move forward were enough to have at least a seed of doubt that perhaps blocking progress was not a strong enough reason to not have this feature. That blocking progress, halting the graph, is a footgun that already exists in a whole bunch of different shades. Now, that may not be a strong enough argument to take it all the way to the end, but it was good enough to get us to say, hey, we want to explore this problem space. And we just punted on deadlock. We said we'll figure this out later. And this is a really fun point too, is you don't always need the answer to every problem in order to move forward with a solution. You just need to identify the problems. So simply saying that we were aware deadlock was a problem and we would try to solve that in a later stage was enough. And with all of that together, we were able to get the TC39 to agree to a stage 1 for top-level await, which means that the committee agreed that this was a problem space we were going to explore. So of course, the next thing I needed to do is figure out how to get it to stage 2. And with stage 1, it was the signal that they were interested, but we really needed to figure out the shape of the solution even further. We needed to walk in with a strong idea of how we were going to solve this problem. And so what we really needed to identify were the spec changes necessary. So when ESM is executed, it's represented as a graph of module records. So that diagram that I was showing before, you could think of each of those nodes as like a map with information about the module itself. So every single one of these nodes is just a set of metadata. It may have information about where it existed on the file system, where you might find it in the cache, what is the actual binary representation of the data that that module is representing, and it's all linked and it's ready to be executed. And the algorithm for executing is also defined. And the underlying mechanism of how that should be implemented in a VM is also defined. And this is what our spec changes looked like. And so what you'll see that's really fun, the first thing that we ended up doing is we took the code from inside of asyncfunction start, and this is the underlying mechanism that's called inside of the virtual machine when you start an async function. We abstracted it into a new function called async block start. And you'll start to see, hey, writing a spec is kind of like writing code that you can't run. And we just performed that async block start thing. We just essentially copy-pasted all of those steps into its own function. And then we went into the evaluate method. This is like the actual method that's being called when you're evaluating. And we set up promise capabilities. A promise capability is a lower level thing like a promise. It doesn't have all of the like ins and outs of a promise, but it gives something the ability to be thenable, the ability to be deferred, and wait on it. And what we've essentially done here, and it's maybe a little bit esoteric, and we can dig through this later, but this I think is the best example in the module execution, is we created a new promise capability, and instead of just executing the context, we performed an async block start on the context with that promise capability, essentially instantiating every single module as a promise to execute. And what we were able to do then, which is super fun, if I can just find that one bit in here, is this right here, be await. There's actually an abstraction inside of the spec called await that can block execution in the spec until a promise capability resolves. So we actually use await to implement top-level await, which is like this fun recursion that I really like. But essentially, what we did was we made it that every single module that's executing, instead of just synchronously executing and then calling the next one, returns a promise to execute. We await that promise to resolve, and then we execute the next module. And this algorithm supports variant A, but if we implemented another abstraction in the specification itself for promise.all, we could just replace that call to await with awaiting a promise.all of all of those promise capabilities. And in the same way that those 2 bits of pseudocode that I showed you, we could actually convert those pseudocode almost directly into spec language, and it would maybe just work. At least that's as far as I was able to take it so far. I'm working with some much smarter people to help take it over the finish line. But But the importance of the way in which this algorithm was designed was that for going to stage 2, we could actually even punt on a decision between variant A and variant B, because the same basic shape of a solution could solve either of those. So as long as we had consensus that top level weight would either be A or B, and that the algorithm that we had implemented could work for either A or B, that was enough to get to stage 2 that we have a general shape of the solution to the problem. That unblocked those objections. We clarified in the specification that top level await would only ever exist in the module goal, not the script goal, never in CommonJS. And that unblocked all the objections regarding interoperability. We were just going to be clear. There wouldn't be interop. And we deferred to the current behavior for handling deadlock. We kind of just punted on that one again. But we said, hey, there's current behavior for deadlock. If you end up in cycles, it will throw. And we want to at least rely on the current behavior in the specification. And then we're going to run some tests and clarify that before stage 3. And that allowed us to unblock objections related to cycles. And you'll see a bit of a pattern here. Starting all the way back from that original top level await as a foot gun, we identified what are the constraints that people will block on. And we came with a proposal that spoke directly to those objections. Not only did we have to come up with a solution, but we had to directly speak to the objections of people who had problems with it. And in May of 2018, we were able to get top level await to stage 2, which was really exciting. I didn't even think we'd be able to get that far. That kind of brings us to where we are now, which is what's next? How do we get to that next stage? And I personally want to move forward with variant B. But we need to build consensus around those semantics. We still have people who are pretty hard on wanting it to be variant A, and we still have people who aren't even convinced that top level await should be a thing. So building consensus around this will be important. I do think that we're off to a good start. Rich Harris, who wrote that original top level await as a foot gun, recently tweeted that he thinks variant B, which allows some parallel execution, is probably the best trade-off between the various different goals, specifically because async immediately invoked functions expressions everywhere are almost worse than not having top level await. And we're going through a variety of examples specifically to define the semantics of deadlock. So we are up to about 6 different iterations of how we could identify cycles in a graph and how we should handle that semantic. And the intent is right now to make it fail early. So if you have 2 modules that are awaiting a dynamic import that import each other, it should just throw. That's most likely the semantic that we're going to move forward on. Just don't allow dynamic cycles. That seems to be the easiest way to avoid, for lack of a better term, a bunch of foot guns. And we need to finish writing the spec text, and the text needs to be reviewed and approved. And this is going to be the hardest step, because essentially getting it to stage 3, getting that last bit of sign-off, getting to that next stage, will mean that V8 can start implementing it, that Edge can start implementing it. And that implementation, from what I hear and from what I've been looking at, is actually not even that hard. It's the semantics and consensus that are the hard part. So a little bit of a waiting on how we could imagine this works out. So as long as you are all patient and I'm persistent, I'm hoping that we get there. And that persistence is important. And I think I just want to relay that idea from earlier, that your intuition may be to fix problems at the layer of abstraction that you have control over. If one of your dependencies is broken, you may just monkey patch it in the scripts that you control instead of sending something upstream. If something upstream is broken because the language has a problem, you may not try to engage in the standards process, or you may not even have the platform to do so. But I want to try to empower every single person in this room. It takes time and it takes determination, a bit of luck, and a bit of support. But don't let anything stop you. If there's things that you want to do and people tell you that you can't do it, do the research. Maybe you can. Don't let anyone tell you what you can't do. Thank you very much. This is a surfing dog.
Wonderful. Thank you so much. Thank you, Myles. We don't have a lot of time for Q&A, but since Charlie's got a couple of things to plug in, I'm going to take the opportunity and steal you for just a couple of minutes, if that's
absolutely.
okay. Come and take a seat on one of these core strengthening wobble seats. I'm getting in good shape throughout the day for this. It's such a fascinating thing to see, like a little glimpse behind the curtain of how some of these things come to life and like the workings behind the scenes. And you talked about how people get involved or how TC39 works and the different ways you can participate. What's the easiest way for me to get involved? So without getting like super involved in an organization or becoming a member, can I get involved in the conversation? Can I go somewhere and see the conversation and chime in?
Yeah, if you go to github.com/tc39/proposals, you'll actually see a list of every single proposal and what stage that they're in.
In GitHub?
In GitHub.
In GitHub.
And
okay.
if you go to that link and you see a proposal that you're interested in, click on it, read it, open an issue, open a pull request. Anyone can contribute on GitHub like any other project, so if there's something that you're interested in, just get involved.
Nice. And do you think, is there a particular phase of that process that is more valuable to get involved in? I mean, is it like right from the straw man right through to the proposal, the draft bait? Is anywhere good to get involved? Do you think you can learn at every stage of the way? I
think it depends on your skill sets, but there are things that people who are just getting started can contribute all throughout. You don't need to know how to write spec text. You can write a Babel transform earlier. You can write, there's a thing called web platform tests, which are compliance tests for these features. There's lots of different ways that you can pitch in from varying skill levels. Okay, awesome. I mean, there's so many questions I'd like to ask you, but I think on that note and your kind of closing note of empowering every person in the room, knowing you can do that, everyone please make him say your thanks, please, for Myles. Thanks, Myles. Thank you.